Hello everyone. The following presentation is about the advent of the current femto era. It describes the works and the findings, especially the femtocell scenario simulations have been exfoliated in this project presentation. My name is Sankalp Mohanty. I'm a graduate student at the University of Florida. Let's start with describing the evolution of the cellular systems in particular. We all know a single base station can be further subdivided into numerous macro stations. This can further be propagated as a single macro base station can be further subdivided into several smaller femtostations in particular. We know as the current throughput, demand and usage is going on increasing, the cell size has a generally decreasing trend. From 2G we are now established in almost a 4G network system. This graph shows the current traffic trend in comparison to the future traffic trend expected in communications area. You can find that the outdoor communications is predominant in current traffic, whereas in future both home and work will take the major chunk of communications, and femtocell increases coverage in smaller establishments like work and home. So this kind of a femtocell era is quite important and going to be a much more predominant factor in the future. Moving forward, what exactly is a femtocell? A femtocell can be best described as a small cellular base station designed for use in residential or small business environments. It connects to the service provider's network via a broadband, such as a DSL or a cable, and it typically supports 2 to 5 mobile phones in a residential setting. A femtocell allows service providers to extend service coverage inside of our home without the need of expensive cellular towers, especially where access would otherwise be limited or unavailable. A femtocell is sometimes referred to as a home base station or an access point base station. It is also sometimes called as a 3G access point, a small cellular base station, or a personal 2G to 3G base station. Moving forward, what are the needs of femtocells? To start with, a macro cell cannot provide good signal strength for indoor coverage. Femtocells, on the other hand, enables higher capacity, so gives us a very high data rate. Also, femtocells help in reducing the overall power load on the existing macrocell networks. To summarize, femtocells are low-power wireless access points that operate in licensed spectrums to connect standard mobile devices to a mobile operator's network using a residential DSL or cable broadband connections. This entire can be diagrammatically explained in this layout of a femtocell, where we find a particular femtocell in a house connects the mobile phones, the PDAs, the laptops, all the electronic devices through a broadband router directly to the internet. So similarly, all the femtocells in neighboring areas is also directly connected to the internet, which connects to the macrocell through a femtocell gateway. Some of the benefits of femtocell in general are: for operators, it is viably a low-cost solution, and it also improves reliability much more. Also, femtocells can lead to an increase in coverage and capacity while reducing the macrocell backhaul capacity requirements. Also, femtocells work pretty well with existing handsets, and there's no need for expensive subsidies on dual mode such as 3G plus Wi-Fi, etc. Moving forward, femtocell from a consumer perspective also is a win-win situation, because femtocells also lead to reduction in costs with no need for expensive new devices installations. Also, it gives you better indoor coverage and a superior quality without the change in the phones. So in general, it is simplicity with a one phone, one mode and one number era. Moving forward, there are various radio deployment issues in femtocells, in particular generations. There are three respects in which radio issues differ from femtocells as compared to macro base stations. These three issues are: First one being the required coverage deliberately limited to the area of the group or a small office associated with a given user group for femtocells. Also, there is interference between macro-cells and the femtocells, and it is controlled via entirely automated means rather than via manual planning. The third issue being the cost of femtocells must be minimized, so radio specifications which drive excessive costs without significant performance benefits must be avoided. Moving forward, the interference analysis, we have two different kind of interference occurs in general with a femtocell deployment. One is the cross layer, another being the co-layer. In cross layer, we have two different network layers, and there occurs an interference between a femtocell and an existing macro-cell network. What happens is the aggressor being the femto access point and the victim being a macro-cell user, both of them being in different network layers. Their interference occurs is called as a cross-layer interference. Another interference that occurs in general is a co-layer interference. This is in general a femto-femto interference where we find both the accessor and the victims being femto access points, but both of them being neighboring to each other belonging to the same network layer. There are various ways of overcoming interference in general. The very first way is the usage of sectoral antennas at the femto access points. Also, we can use a dynamic selection of predefined antenna patterns to reduce power leakage outdoors and thus mitigate interference to a much lower level. There are some hardware-based approaches also, but they do lead to an increase in the overall femto access point costs. So they're not that a viable solution. Some power control algorithms can also be used, and also we can employ efficient sub-channel allocations to overcome the interference that generally occurs, both the cross-layer as well as the co-layer interferences that occur due to femtocell deployment in a macro-cell layer network. Moving forward, let's talk about the various path loss models. To analyze a femtocell performance, it is very important to study the coverage, and path loss models sometimes help us in generating a coverage of a femtocell. Here we assume the aggregate loss through furniture, through internal walls, and the doors are represented by a path loss exponent called N that depends on the type of the building. This following equation here gives the path loss model. First we have N is the path loss exponent and LF of NF being the floor penetration loss. The total loss can be calculated as the shadow fade margin loss and the loss that represented through the outer walls together with the one that we calculated earlier. All three combined gives the total loss that can occur in a radio convergence area. The coverage can be calculated where the maximum acceptable path loss required to deliver an adequate pilot channel signal quality is given by this equation, where Pmax represents the maximum power transmitted to the femtocell and NUE represents the user equipment receiver noise power, and PCPICH represents the proportion of femtocell power allocated to the pilot channel. When we combine all these parameters with these particular values, with LFM being equal to 7.7 dB and using one floor at 9 dB and two floors at 19 dB differences, and this following path loss component as 2 and the noise figure as 7 dB, we get the following simulation that can be graphically obtained. The first simulation describes the femtocell coverage on the same floor, whereas the second one describes when there is a gap of one floor with the noise margins being as different as 20 dB. Femtocells can also cause a degradation of the macro cell performance, but the overall performance goes on decreasing. This graph here describes the throughput analysis with respect to the number of femtocells. As you can see, the throughput of a macro cell can generally go on decreasing from the simulation, but the overall performance due to the presence of a femtocell in an existing macro cell network goes on increasing further. Throughput can be calculated as this equation denominated here using various signal to interference ratios. So what we can find, and these parameters as denominated here, when totally incorporated, we can find that for a cellular OFDMA system with supposing 100 active users and a single macro cell serving all the 100 users, we need actually 50 femtocells with 2 active users each in a femtocell. Then this simulation that can be shown here depicts the cumulative distribution function of the downlink throughputs for both the macro cells and the femtocells. Here you can find that the femtocells with number of users increasing from 10 to 100 and macro cells with users from 0 to 10 to 100 have this kind of a cumulative distribution function. The first 3 cumulative distribution functions denominate the macro cell simulation, whereas the bottom 2 CDFs represent the femtocell distribution. As you can find, the increase in the number of femtocell users in an existing macro cell network does not hamper the macro cell throughput as much, and we get a better signal to noise ratio as compared to the macro cell layers. To enumerate the simulation results, we have the drop in the macro cell signal to noise ratio is a result of the additional interference caused by 10 or 100 active femtocells, which is pretty minimal in nature. The drop in the macro cell signal to interference noise ratio is pretty minimal, which is essential for a successful femtocell deployment. This is due to the low transmit power in the downlink used by the femtocells and also due to the separating walls. There is also a higher indoor signal to interference noise ratios as a result of the small distance to the femtocell and the effect of the walls, which shields the signal from the interference. It is also shown in the previous simulation that increasing the number of femtocells from 10 to 100 does not significantly affect the downlink femtocell signal to interference noise ratio. This is due to the fact that the small cell sizes are used and the strong wall separations between the houses. So to summarize, a large number of femtocells can be deployed in the same frequency band as the existing macro cell networks without a significant downlink performance degradation of the existing macro cells when public access to the femtocells is granted. To conclude, as we can say, the wireless capacity has been doubling every 30 months for the last 104 years. So this translates approximately to a million-fold capacity increase since 1957. So there is a kind of a 25% improvement from wider spectrum allotment. There is a 5% improvement by dividing the spectrum into smaller slices. There is also a 5% improvement in the existing capacity by designing better modulation schemes. But we can get almost a 1600 times improvement or a gain by reducing the cell sizes and the transmitting distance. So this enormous gain reaped from smaller cell sizes arises from the efficient spatial reuse of the spectrum, or alternatively a higher area spectral efficiency. Thus, usage of femtocell in coming era can increase the capacity of the wireless communications multifold times. These are some of the references that are used in this project simulations. Thank you and have a good day.